When one travels to the Intermountain West of the United States, it is not uncommon to find what are known as ghost towns, remnants of human habitation hastily constructed and quickly forgotten. Some of these were built by men sinking their fortunes among the various gold and silver rushes of a landscape rich with natural resources. The vast majority, however, were built by the various railroads that crisscross the vast open expanse of country to transport raw materials east and finished products west. Along these miles of tracks were scattered small settlements. Some were built to house the workers that maintained the tracks, while others served as way stations to load coal and water to fuel the boilers that drove the steel wheels over the polished rails. One such town was a place known as Separation, Wyoming, and on July 29, 1878, it served as a gathering place for some of the most talented scientists in the United States. Separation lies along the old rail line that climbs from Cheyenne towards Laramie up to the Continental Divide. Halfway between Rawlins and Creston, it was a little bigger than most such places, in that it had a post and telegraph office in addition to the usual train servicing accoutrements. Nowadays, you have to look for where it used to be, just south of Interstate 80, as you travel east about 13 miles before you get to Rawlins. The town is gone now, sold by a company that switched to diesel locomotives and mechanized maintenance of the tracks to someone looking for cheap scrap and pre-constructed buildings. In 1878, though, it was a much more interesting place, because its geography provided a place of shelter from the ever-present Chinook winds that came down from the Rockies and stirred up dust that would darken the sky and cover everything including cameras and telescopes. This, of course, wouldn't have been an issue on most days, but in July of 1878, there was something just a little bit different. The rail line between Laramie and Cheyenne traveled along the path of a full solar eclipse, and so astronomers all across the nation, one so recently having celebrated its centenary, were looking to make a name for themselves by observing another sort of ghost. Some 20 years earlier, a French astronomer had predicted that there was another planet, one he called Vulcan, whose orbit was so close to the sun that it could only be observed during an eclipse. And so these men had set out to see if they could capture an image of it, or at least sight it amongst the revealed stars during the totality of the event. Among them were three famous figures of note. One was the inventor, Thomas Edison, who had made the trip out west to see if he could test a piece of equipment to measure the infrared radiation of the solar corona. Another was the U.S. Naval Observatory's premier astronomer, Simon Newcomb. The third was the director of the University of Michigan's Ann Arbor Observatory, James Craig Watson. The three men set up their equipment on a depressed plane in hopes that it would protect them from the wind and dust. While the unforgiving environment played havoc with their equipment, the men were able to finally make their observations. In an eclipse, the period of totality, when the sun is completely obscured by the disk of the moon, there's only a few minutes to make observations, and so they must be done quickly and efficiently and under a great deal of pressure. As he began his scans of the region around the disk of the moon, sweeping his telescope back and forth, Watson quickly found an object he did not have on his charts. Soon he continued to scan, and then he found another, which he marked in his record just as the eclipse ended. Next to Watson, Newcomb was scrambling to make his desired observations. While things had started out pretty roughly for him with the failure of one of his telescope's motor drives, he recovered quickly and professionally. After a minute of observing the solar corona with one instrument, he switched to a second telescope, designed specifically to look for this inter-Mercurian planet, Vulcan. Only at the last possible moment did he see something that might not be on the maps, but then it was all over. As the two men compared notes, Newcomb found that his candidate object was, in fact, on the star charts, and that it did match Watson's second object, thus eliminating it as a possibility. However, the first object of Watson's seemed to be unaccounted for, and so there was jubilation in the camp that day at separation. Watson was sure he had seen Vulcan, and soon announced his discovery to all the world. The response, however, was, shall we say, tepid. No other observing group along the path of totality had seen what he had. Furthermore, it seemed that Watson's methods had been a bit imprecise and more than just a little dubious. His rival astronomer, C. F. H. Peters, spared no feelings when he wrote a scathing rebuttal of the findings, one that, while overly harsh, or at least thought by many, was broadly accepted by the astronomical community. The ghost planet had once again been sighted in an Old West ghost town, but to understand the impact of this failure to find what should have been there, and yet didn't seem to be, we need to go back some 30 years. Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a many-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery. Series 3, Finding Our Place. Episode 30, False Gods. At the end of 1846, Urbain Le Verrier was in a very good place in his life. His discovery of Neptune had catapulted him to the place of being the top astronomer of his generation. Louis-Philippe bestowed upon him France's Legion of Honor, and the French government made him an offer that he couldn't refuse. They asked him to submit a proposal that outlined his future research intentions and what he would need in terms of support in order to achieve them. His response was to complete the project started by Simon Laplace. He wanted to, quote, encompass in a single work the entire ensemble of the planetary system, reconcile and render everything harmonious, if possible, and when this cannot be done, to declare with certainty that there exist causes of perturbation still unknown, whose origins are then, and only then, revealed. End quote. It was both a simple and startlingly complex project that he proposed, especially for someone who wasn't actually much of an astronomer and only a reasonably good mathematician, as opposed to Laplace, who had been his generation's mathematical savant. So what would this project involve? Well, first off, Le Verrier would have to gather all of the existing observations of all of the planets. He would then have to build a system of equations for each one that would take into account the gravitational influences of each of that planet's neighbors on it until all of the interactions were accounted for. Then, from these observationally informed mathematical models, a table of the motions of each planet would have to be produced. Finally, these predictions of the positions of each planet at any given time in the future would have to be compared against the actual observed positions to see if they were successful. Straightforward, yes, but also an enormous amount of work. Le Verrier estimated that it would take he and an assistant over a decade to do the work. The Ministry of Public Education reviewed the proposal and quite rightly saw that what Le Verrier was asking for was really a very small sum in the overall scope of the finances of the French treasury. Thus, the project was approved, and Le Verrier, the one-time chemical engineer working on phosphorus matches, now had what was effectively lifetime tenure to pursue his scientific interests. But he didn't get started right away. There was something of a victory lap to take place. You don't just discover a planet and then not allow your colleagues to, shower you with praise. In person. For about a year. And just as that was winding down, it turns out that the revolutions of 1848 began to get wound up, and over the course of the next 2 years, Paris was roiled with conflict and turmoil until the last Bourbon king was expelled from the throne and the Second Empire was inaugurated under the rule of the nephew of the Little Colonel. Fortunately for Leverrier, he managed to keep his head down and stay out of trouble and harm's way, and so, in 1850, Napoleon III confirmed the government's intention to fund the research, and things got underway. So why would Leverrier succeed when others seemed to struggle so profoundly when it came to this sort of thing? Like we said, unlike Herschel, he wasn't really a very good observer, and he fell short of the talents of the other continental mathematicians of his time, such as Gauss. What the Frenchman possessed is what is sometimes called in physics and astronomy intuition. He had a way of just sort of seeing the best way forward through a thicket of observations and equations, an instinctive sense of which avenues and paths were most likely to yield results and which would lead to dead ends. He could look at the formulas and numbers and in his head construct the physical systems they modeled so clearly that he knew what was and wasn't the right answer before anyone could show it. It's this sort of thing that can separate a great scientist from a good one. He had shown this when, in working with calculations on the deviations of Uranus's orbit, he was able to simplify the tangle of expressions by making assumptions about what the size, mass, and rough distance the perturbing planet would be from Uranus. He also knew the best way to simplify his mathematics so that he could make the difficult-to-solve nonlinear equations linear and tractable. He made up for his lack of mathematical chops by being able to understand what the solution should look like before he actually had the solution. And that is a very powerful thing for a scientist to be able to do. Shortly after getting started on his new project, he was once again able to put this talent on display. As you will recall from our episode on planet hunting, when astronomers realized that there was a planet missing from the Bode's Law sequence in between Mars and Jupiter, they went looking for it, and in 1801 found first Ceres, and then in 1802 another world that was named Pallas. Not long after that, a few other objects were also discovered in roughly the same orbit. None of these worlds were really large enough, and so the discoverer of Pallas, Heinrich Olbers, suggested that perhaps the worlds were just fragments of a larger primordial planet that had undergone some sort of destructive catastrophe. So sure of this hypothesis was Olbers that he named the progenitor world Phaeton, after the son of Apollo, who was struck down by Zeus, or Jupiter depending on your cultural tradition, from losing control of his father's chariot while flying it across the sky after having stole it. It was a lovely and elegant hypothesis, and it not only explained how things already discovered got there, but also predicted that many, many more fragments would be found as more and more powerful telescopes and detecting techniques were developed. An elegant hypothesis indeed, at least until Leverrier came along and with his intuition slayed it with an ugly fact. That ugly fact is something we call gravitational resonance. What Leverrier realized, or sort of saw as he worked out the initial observationally based orbital calculations for his full model of the universe, was that for every 17 times Pallas went around the Sun, Jupiter went around 8 times. Now, I know this seems like a kind of weird ratio, this 17 to 8 sort of thing, but what Leverrier understood was that on a regular basis, Jupiter's mass would tug on Pallas's mass. Now, if Jupiter had been a small world, say like Mars, or had been further away, like Saturn, that might not have mattered a whole lot. But since it was both relatively close by and very, very massive, that regular gravitational kick would be pretty big. Big enough, Leverrier realized, to keep Pallas from being able to get close enough to any of the other chunks of matter nearby to pull them into it and thus get bigger. Once he saw this, he looked at the orbits of the other large worlds and found similar effects. The asteroid belt, as we now call it, was not the remnant of some shattered world. Rather, it was the leftover pieces of the early formation stages of the solar system, kept from coalescing by the tidal influence of the king of the planets. There never had been a Phaeton. just the unconsolidated protoplanetary fragments and planetismals left over from the time when the solar system was very young and still forming. In time, as Olbers predicted, when astrophotography techniques were developed and perfected, the number of known asteroids, a term coined by our friend William Herschel, exploded. My colleague at Gordon State College, Dr. Richard Schmude, was recently honored for his work on Earth-bound planetary observations by having one of these named for him. Recently, the NASA Dawn mission settled into a low circular orbit around Ceres to give us a glimpse of what most of the objects in the inner solar system might have looked like as they originally collided with other similar objects and grew to their planetary sizes and compositions. What it found was a densely cratered world made of silicate rock and watered ice that has been scarred by hundreds and thousands of impacts great and small. As Leverrier's work progressed, he found that his models for the outer worlds, built for his search for Neptune, held up well, and so he turned his attention back to the inner worlds, who he had last worked on in 1845. In the years since, a bevy of better observations had been made that allowed him to not only make better estimates of the masses of Venus, Earth, and Mars, but also made it possible to improve on the calculation of the astronomical unit, that distance between the Earth and the Sun. What didn't get better was the orbit of Mercury. A decade before, the transit observations had shown Leverrier's predictions to be off some 18 seconds of time when determining the time of the start of the transit. Now things were even worse, and so he set out to account for it. To fully understand what Leverrier found, we have to do just a bit of orbital dynamics. If we go all the way back to Kepler, you'll remember that the first of his 3 laws of planetary motion said that all of the planets move in ellipses with the sun of one focus. What that means is that the planet's orbital path through space is an oval-like shape known as an ellipse. Okay, so far so good. The thing is, though, that the sun isn't actually at the center of the oval-like ellipse. It's shifted off to one side of the center along the long axis of the ellipse. Now, for most planets, this shift isn't very big. In fact, it's almost imperceptible, except for Mercury and Mars. For Mars, it was big enough to allow Kepler to work out the nature of its orbit first and thus come at his discovery of the elliptical nature of planetary orbits. It would have been even more noticeable for Mercury, except that since Mercury is only a third of an astronomical unit from the Sun, it's really hard to get good measurements because the planet is lost so often in the Sun's glare. Now, when Newton worked out the orbits of the planets from his laws of motion and the universal law of gravitation, he did so for each planet in sort of isolation. With the exception of the Moon, he never attempted to try and figure out what the effect of the other planets' gravitational attraction would be on the various other worlds in the solar system. This isn't to say that he was completely unaware of the effect, just that he never went all in for the calculations and tried to work everything out. A man can only do so much in his lifetime, you know? That's what Laplace had done to a degree. As it turns out, one of the effects of a small tug from another world can have is to cause the elliptical orbit to what is known as precess, as astronomers call it. What this means is that the long axis of the orbit begins to pivot or turn through an angle pinned at the sun. One way to sort of get a sense of this would be to take an egg and lay it on its side and then slowly rotate it around the point that touches a tabletop. If the ovoid outer shape of the egg were to somewhat approximate the shape of the orbit, you can sort of see the precession of the long axis of the ellipse as the line from the top of the egg to the bottom rotates around that contact point. And by the way, if this is a little confusing, we'll try to put a picture out on our website, thescientificodyssey.typepad.com, for you to get a sense of how this precession actually works and looks. This is what was causing the error in that predicted motion of Mercury. If Leverrier could account for all of this precession, then Newton's universal law of gravitation was once again confirmed. If not, that difference would have to be accounted for. And so, after having engineered his appointment as the director of the Paris Observatory and working to modernize and update its outdated equipment and procedures, he set his staff to calculating. By 1859, they had their answer. They could account for all of Mercury's precession except some 38 arcseconds a year. Once the tiny gravitational perturbations of Venus and Jupiter and all of the other planets were calculated, there was a tiny fraction of precession that couldn't be accounted for. Mercury, as had once been the case for Uranus, stood in contradiction to science's most powerful and best tested framework. And just as been the case for Herschel's discovery, Leverrier suspected that there was another, yet undiscovered world responsible for the discrepancy. Relying once again on that uncanny intuition, he put forth the idea that the world had to be closer to the sun than Mercury, so close and so small that it had escaped detection. Given those conditions, there would be only one name for that world: the Roman god of the forge, husband of Venus and maker of Jupiter's mighty bolts of lightning, Vulcan. Such was Leverrier's esteem among the astronomers of his time that no one really doubted him. The question became not so much was there a planet, but rather where to look for it. As he had done with Neptune, Leverrier began by making a few well-informed assumptions. The world probably couldn't be too big, or it would have been seen by this time. Like everything else in the solar system, he thought it probably had to orbit in a plane that was pretty close to being lined up along the sun's equator. And, as a first guess, he decided that Vulcan was maybe halfway between the sun and Mercury. As he did the calculations, Leverrier came to the conclusion that it was just as likely, actually, that instead of there being one planet, there might just be a small group of smaller asteroids that did the work of perturbing Mercury's motion. But this wasn't exactly something the astronomical community was very excited about. Nobody got really excited about finding a whole bunch of small asteroids. It was finding a planet that would make a man's career. The best hope of finding the object or objects would lie in one of two avenues. The first was to observe the disk of the sun and hope to catch Vulcan or the asteroids as those things transited across the disk. This was a doable task, but fraught with difficulty, as it would require separating out the heretofore unseen world from the various sunspots that were often observed on the face of the disk. Given that the planet would cross the sun's disk faster than the sun actually rotated, it wouldn't be possible to tell the planet from the sunspots, however, but it would take very good observation. The other method would be to wait for a full eclipse of the sun and then hope to catch the world when it wasn't crossing the sun at that time, and therefore it would be seen as a bright object not found on the star tables of the region in which the sun eclipse took place. When Leverrier published a short account of his work on September 12th of 1859, the French Academy's secretary, Hervé Faye, recognized the solar eclipse solution and wrote about it to the Academy's members. The next full solar eclipse was to take place on July 16th of 1860 over North Africa and Spain. And so, the gears of the scientific establishment began to turn in order to send observing teams to various locations along the path in hopes that the planet could be found. However, what happened next was one of those things that you can never predict. Out of nowhere, a sighting of the planet was announced. Edmond Modeste Lescarbot was a modest, humble country doctor in the small town of Areges in Beauce, located between the Seine and Loire rivers, about 70 miles south of Paris. He had caught the astronomy bug early in his life, and unlike so many, he had never lost it in the years of growing up and becoming a physician. Instead, for him, it became a comforting distraction from the banalities of practicing his trade in a remote part of the country, far from the bright lights of the city. When he had a chance, he would steal away from his business of attending to patients to a low stone barn that he had built, which housed a more than passable observatory. Under its dome, he kept a very serviceable 4-foot-long refracting telescope with a 4-inch objective lens and the necessary instruments to fix an object's position, and some timekeeping devices to allow him to make very precise observations. On Saturday of March 26th of 1859, almost 6 months before Leverrier would announce his results, Lescarbault was engaged in his usual routine when he took a chance during a break in the patient's list to head out to the telescope to make some observations of the sun. By the way, it's here that I need to make that standard cautionary remark to not try this at home, kids, unless you have a specially constructed telescope designed specifically to look at the sun, or you have a high-quality front-end solar filter. Any sort of magnification of the sun's light, either with binoculars or a telescope without such protective gear, will almost certainly result in some sort of damage to your eyes and is actually pretty likely to cause blindness. Fortunately, the subject of our present story took such precautions. As he turned the telescope upwards and towards the sun, he saw just inside one edge of its disk a small circular spot that looked different from a sunspot in that it was far more regular, far more circular, without the sort of fuzziness around the edges. It was about 1/4 the diameter of what Mercury's disk would have been in transit, and so he realized that this really was something a bit different. Immediately he started his pendulum timer and counted the number of seconds it took for the object to move the same distance across the sun that it had already moved before he had actually been seeing it, thus establishing the time of day that this object had begun its transit. 3:59 and 46 seconds p.m., plus or minus about 5 seconds. In between a new patient or two coming in, the doctor kept an eye on the small circle as it traveled across the sun until it finally passed over the other side and disappeared from view. The total time of the transit, the time it took for that object to cross from one edge of the disk to the other, was 1 hour, 15 minutes, and 9 seconds. He realized that he had seen something, and so he made good notes about the event, and then did nothing. For 9 months. Again. I don't know what it is with the French sometimes, but they don't seem to get so excited about discovering things. Anyway, finally, near the end of the year, he wrote to the Paris Observatory to tell them of his observation. He had seen the article on Leverrier's work and decided the great man should know of his observation. When Leverrier read the letter, he was astounded. An amateur seemed to have found proof of his hypothetical Vulcan before all of the world's most celebrated astronomers had, and before anyone had had the chance to try the solar eclipse method. Needing to interview the doctor in order to establish the facts of the observation, Leverrier traveled to the town with a single assistant to examine the instruments and test the doctor to make sure he wasn't concocting the story or was a bumbler. On New Year's Eve, the meeting took place, and after some fairly rigorous questioning, at least according to Leverrier's later rather dramatic account of the event, it was determined that Lescarbault, the country doctor, had in fact seen and reliably measured what he had reported. It was a huge discovery, and as you might expect, Lescarbault was catapulted to fame and soon was also awarded the Legion of Honor. While welcomed, the fame would soon pass, and the doctor would live out the rest of his life, working to improve the health of the members of his small town. Leverrier, on the other hand, now had a set of observations with which he could more tightly constrain the orbit of Vulcan, and so he set out to construct the needed mathematical model that would help predict future transits and also allow eclipse watchers to look for the world. The results of these calculations was an object that orbited the sun with a period of about 20 days and would never be more than 8 degrees from the sun in the sky in terms of a maximum elongation, thus making it almost impossible to observe the object using traditional means. Fortunately, it seemed that the planet would transit the sun's face between 2 and 4 times a year. Now, before we go any further, I imagine a number of you are asking yourselves a really good question at this point. If all of this stuff was going on in the late 1850s and a planet was observed, why haven't I heard of Vulcan? Well, at least, outside of a certain popular science fiction franchise. If Leverrier's application of Newton's laws predicted it, Unless Garbau's observation proved it, why don't we learn about 5 inner worlds instead of 4? Why don't school kids create murals with this tiny innermost planet inside the orbit of Mercury? Well, that's a really great question, one that takes us into the heart of doing science. As we have seen, beautiful hypotheses, no matter how elegantly mathematical, require experimental or observational confirmation. That experimental or observational confirmation has to be made by several independent observers to be considered to be actually factual by the scientific community. Only when this takes place will the thing become a fact and the hypothesis that predicted it be confirmed. The French doctor's report was a strong piece of evidence, but he had been the only one who had seen it. What needed to happen was that other astronomers would have to observe additional transits or spot the planet during an eclipse. As word got out, the popular press across Europe and America trumpeted the news and called for additional efforts to confirm what was sure to be true. The discoverer of Neptune had said so based on the most enduring scientific framework ever created, the laws of Newton himself. The problem is, the confirmation never really materialized. While there would be a few more possible sightings, most attempts to catch the planet as it crossed the sun failed. Soon, a pattern seemed to emerge. When seen, the observation of the planet was something of an accident, observed when looking for something else, or at a time not predicted by models. On the other hand, when well-organized astronomical efforts were mounted, as was the case with the 1860 observation, and these efforts lasted oftentimes over periods of weeks, Vulcan remained elusive. It was never seen. Models were changed and orbits recalculated, but whenever a prediction was made, it failed. As better techniques were developed to record astronomical events, namely astrophotography, Vulcan became even more shy. When, in 1869, an American amateur astronomer and photographer, Benjamin Gould, tried to photograph the region around the sun during a total eclipse, he found nothing but what was expected. As the years wound on, the sought confirmation never came. So what are we to make of this? I think we all know what's supposed to happen at this point, at least if we understand the scientific process of inquiry. Leverrier's hypothesis of an inner world had failed over and over and over again. Even with the later events at Separation, Wyoming that were discussed in the introduction, Vulcan was never reliably found. What's really remarkable was how long the search for it went on, even after the predictions had failed so many times previously. According to the methods established some 50 years earlier about how science was to be practiced, Vulcan should have been consigned to the trash heap far sooner than it was. So why didn't that take place? Well, that has to do with what getting rid of Vulcan or some other inner asteroid kind of model implied. Mercury's calculated orbit still didn't match the observations, and that calculated orbit was based on Newton's laws. If there isn't a planet or something like it, the implication was that Newton's laws were wrong somewhere. The failure to find Vulcan brought into question what up to that point had been so very successful. According to some accounts of the way science should be done, the fact that Mercury didn't follow precisely the orbit set forth by Newton's laws, that should have invalidated those laws. And yet, they had worked so well for so long. As such, attempts were made to very slightly modify the universal law of gravitation, but every time a tweak was made that fixed Mercury's orbit, it broke some other confirmed prediction. Even more powerfully, though, there was nothing better to replace Newton's mechanics. It's not so hard to throw out a scientific idea when there's another option that better explains the observations. Getting rid of it when there's nothing else is really tough. Newton's ideas had worked for nearly 200 years on every single problem they had been applied to. They had survived the atomic revolution in chemistry and the rise of thermodynamics. Tossing them aside was not something to be done lightly. So, while France and Germany went to war over German unification, something that would end the Second Empire. And as Mendeleev and Myers each put together an organizing framework of a periodic table of elements, the astronomical community struggled to come to grips with the planet that was not there. Many continued to search with a flurry of activity centered around an eclipse observed in China in 1876. A year later, Verrier, suffering from liver cancer, would pass away on September 23rd, 41 years to the day after Gale had observed Neptune. He died still believing that Vulcan was there. It would be just 2 years after that Chinese eclipse that the tiny abandoned rail town of Separation would host James Watson, who would make his eclipse observations there, and he too would be convinced that he had seen Vulcan. Unfortunately, no one else did, and he too would die within a year and a half of his observations, of course, also believing that he had seen the planet. However, the lack of confirmation at what had been the most closely observed eclipse in human history was the signature on the death certificate for Vulcan as well. Yet, like the ghost of some Shakespearean tragedy, the discrepancy it had been invented to solve remained to haunt astronomers and physicists in their sleep. For the next 40 years, it would rattle its chains every so often to remind those who placed so much faith in Newton that there was something rotten in Denmark. It wasn't until a professor in Zurich saw a workman fall from a rooftop that the mystery would be unraveled. That, however, is a story for a later time. Our last piece of narrative in this episode is also something of a mystery. As the century turned from the 19th to the 20th, the Victorian world was in full bloom. While certainly a time of great disparity in wealth and opportunity in many places, the advances of science were now evident for all to see. The ability of astronomers to measure and calculate the orbits of the planets, Mercury notwithstanding, was extraordinarily precise, and once again, as the precision got better, all was not well. This time, the problem was with Neptune. As had been the case with Uranus, its orbit did not seem to be behaving exactly as expected. While the deviations were small, they seemed, at least to some, to be very real, and so two men in particular began to advocate for the search for Planet X, as it was sometimes called. One of these men was the astronomer William Henry Pickering, of whom we will have a great deal to say in a later episode. The other was a wealthy Bostonian businessman and mathematician, Percival Lowell. While we don't have nearly enough time in this episode to do Lowell's biography justice, he had made a national name for himself, popularizing the idea that Mars was inhabited by a canal-building race of beings after an Italian astronomer had reported observing canali, or channels, on the planet. Lowell had built an observatory in the high, dry air of the then-frontier town of Flagstaff, Arizona, and had dedicated it to the observation first of Mars and then Venus. As a side note here, if you ever have a chance to visit the Grand Canyon, I would heartily recommend taking a side trip to the Lowell Observatory. It's a truly wonderful facility, and if the original telescope facility is open for touring, you'll get to see how a man for whom money is no object builds an observing space. The original telescope through which Lowell made his Mars observations is a refractor, and it truly looks like something right out of a steampunk graphic novel. About 20 years ago, I had the chance to look through the telescope at Mars during opposition, and I have to say that it's pretty amazing that Lowell was able to see much structure on the surface of the planet, much less infer water-transporting canals to a dying civilization. By 1906, the focus of the observatory's work began to shift to attempting to find Planet X. In 1909, Pickering and Lowell had made enough calculations based on the methods we've already discussed in some detail with respect to Verrier, and had come up with several search regions. For the next several years, until his death, Lowell searched in vain for the phantom object, as the astronomical world wondered if this wasn't another wild Vulcan chase. Over the next 10 years, the search stalled and Pickering moved on to other things. But in 1929, once some legal issues with Lowell's widow had been resolved, the search resumed. Just as things were getting going again, the observatory's new director, Vesto Melvin Slipher, received a sheaf of drawings from Mars and other objects. Impressed by the detail of the work, he returned to the envelope and found that they had come from a small Kansas town and had been drawn by an unknown amateur astronomer and farm worker by the name of Clyde Tombaugh. Impressed enough to write back to offer Tombaugh a job, the young man arrived in Flagstaff, having spent all of his money to buy a one-way ticket to that one-time frontier town. Slipher set up Tombaugh to work using a new instrument known as a blink comparator. The way this worked was that Tombaugh would take a picture of a small section of the sky with a 13-inch reflecting telescope equipped with a camera. Several nights later, he would return to the same place and take another picture. It was really work that required amazing attention to detail to make sure everything lined up just right. These pictures would both be placed in the comparator, and the observer could switch or blink rapidly between the two, looking for anything that might have moved a small amount. On February 18th of 1930, Tombaugh found an object in a part of the sky suggested by Pickering and Lowell's calculations that moved. Over the next few weeks, the discovery was confirmed, and on March 13th of that year, the 9th planet of the solar system was announced. Shortly thereafter, a contest to name the world was held, with the winner being a young girl from Oxford, England named Venetia Burney, who suggested calling it Pluto. Soon, however, it became clear that the world Tombaugh had discovered wasn't all it was cracked up to be. Over the course of the next 50 years, the estimates of its mass would be revised downward several times, until it was clear that it couldn't be what was perturbing Neptune's orbit. This was confirmed in 1978 when Pluto's moon Charon was discovered, and good, dynamically determined values of both worlds' mass could be calculated. For his part, Tombaugh continued to search for other worlds beyond Neptune until he retired from active research in 1973. In that time, he discovered many asteroids, but he never did find other objects that might fit the type of object Lowell and Pickering had been looking for. Tombaugh would die in 1997, and by that time, new infrared telescope technologies had begun finding objects in similar orbits to that of Pluto that were roughly the same size and composition of Tombaugh's discovery. In 2005, astronomers at Caltech announced the discovery of Eris, a trans-Neptunian object larger than Pluto, which called into question, of course, Pluto's planetary status. It is here that we should take a moment to talk just a bit about what some of the work had been done in these intervening years that led to this conclusion. And this work sort of focused on things regarding the structure of the solar system. As theoretical astronomers began to work towards a more precise quantification of the formation process of the early solar system, it became clear that there would be huge repositories for comets found in the outermost regions of the solar system. While one of these, first suggested by the Dutch astronomer Jan Oort, was a spherical distribution very far from the Sun, his student Gerard Kuiper put forward the idea of an additional belt of comets that would stretch from just outside Neptune's orbit at 39 AUs all the way out to about 20,000 or so astronomical units. This Kuiper belt, as it is known, was thought to be the source of all comets that entered the solar system, roughly along the ecliptic plane of the Sun's equator. In time, astronomers began to suspect that there would be larger objects of a class to which Pluto and Neptune's captured moon, Triton, might belong. This, along with a revolution in telescopic imaging technology that included adaptive optics and remote telescope operation that would allow telescopes to be built at altitudes where infrared cameras could be used, led to the first discovery of a trans-Neptunian Kuiper belt object in 1992. Dozens have followed since. These discoveries have made it clear that Pluto was part of a larger class of objects, much like Ceres had been back in the early 1800s. As was the case then, astronomers began to question its planetary status, and in a move very parallel to Herschel's suggestion that Ceres, Pallas, Juno, and Vesta be reclassified as asteroids, a number of planetary scientists put forth the proposal that Pluto and other similar objects be reclassified as either trans-Neptunian or Kuiper Belt objects. With the discovery of Eris in 2005, the matter was brought to a head, and a year later, Pluto was reclassified as a minor planet along with other solar system objects. So what about the problems with Neptune's orbit? Was this another case of a Mercury-like anomaly? Well, for a long time, that was something of an open question. When the observations taken around the turn of the century were re-examined, the variations were found to be there, but by the 1930s, the planet was actually found to be moving according to its predicted Newtonian orbit. In other words, the small variations seemed to have disappeared. Some scientists suggested that those variations were the result of observational error, though that seems a bit far-fetched given the exacting nature of the methods used to make them. It wasn't until the Voyager 2 flyby in 1989 that new data came to light that provided an answer. The probe carried with it a gravitometer that was able to make very precise measurement of both Uranus's and Neptune's masses. In 1992, the astronomer Miles Standish took these data and reworked the mathematical models of both Uranus's and Neptune's motions and found that they matched to within the level of error of the gravitometer measurements, and so the mystery was solved. Of course, in 2016, NASA's New Horizon mission flew by Pluto, revealing it to be a dynamic and fascinating world for the very first time. Traveling with the probe was a small portion of Clyde Tombaugh's cremated remains with the inscription, quote, "Interred herein are the remains of American Clyde W. Tombaugh, discovery of Pluto and the solar system's third zone. Adele and Muron's boy, Patricia's husband, Annette and Alden's father, astronomer, teacher, punster, and friend." End quote. It is at this point, at the close of our episode, that I choose now to walk where angels, or at least sane astronomers who don't want to end up on the receiving end of a lot of angry emails, fear to tread. A couple of episodes ago, I asked the question, what is a planet? As I hope you've gathered over the course of this first part of our Finding Our Place series, the answer to that question has changed quite a bit over the course of human history. Over the years we've been discussing in this last month of shows, it's pretty clear that the definitions from the time of Copernicus onward haven't held up very well. Now this, of course, isn't Copernicus's fault. The universe is much more vast and more diverse than he ever imagined. In fact, that could be said for many of the men we've discussed. As such, the definitions of a planet in the 19th and 20th centuries lacked a certain precision, something that became all the more apparent as more and more Kuiper Belt objects were discovered in the 1990s and early 2000s. Therefore, in 2006, the International Astronomical Union decided to come up with the definition of a planet based on more scientific criteria. The first was that the object had to orbit the Sun and not something else. This eliminated all of the various satellites such as the Earth's moon. The second criterion was that the object had to have enough self-gravity to pull itself into a spherical or mostly spherical shape and have something that scientists call hydrostatic equilibrium. This ruled out comets and most of the asteroids and smaller Kuiper Belt objects. It is the third criterion that is the most controversial. This says that the object has to have cleared out its orbital path of other similarly sized objects. This eliminated Ceres and Pallas, as well as Pluto, Eris, and the other large Kuiper Belt objects. A new classification was created for those objects that met the first two criteria but failed the last. They were called minor planets. In this, Pluto was demoted, and Ceres and Eris were promoted, and a whole lot of people who grew up reading about a 9-planet solar system were really disappointed. Now, to be clear, Well, this was decided by a vote of the members of the International Astronomical Union. The decision certainly has had its critics. Many point out that the criteria are mostly based on the orbital dynamics of the worlds rather than on their composition. Some suggest that a better third criterion would have been to say that the planet must have what is known as differentiated structure, meaning that the materials that make up the world will have separated into layers based on their density. In this case, the most recent evidence would elevate Ceres, Pluto, and most likely a few other Kuiper Belt objects to planetary status, thus giving our solar system between 10 and 15 planets, depending on what you think is going on in its outermost regions. So what do I think? Well, to be honest with you, I think the entire debate is rather pointless, and so I tend to take a modification of Carl Sagan's position on this. For me, the term planet is an historical anachronism, a holdover from a time when our distant ancestors saw objects move against the background stars in voyages across and around the heavens. In this picture, there are 7 planets from the Sun to Saturn, just as there are 7 days, Sunday through Saturn Day. The Earth is not a planet, just as Uranus, Neptune, and Pluto aren't. This isn't a widely held view, I know, but what I find is that it frees one from the debate over what should be a broadly meaningless distinction. Carl Sagan, in his writings and on Cosmos, called everything a world. From innermost Mercury to outermost Pluto and beyond, everything was a place worth knowing and exploring. From giant Jupiter with its many varied moons to the smallest comet, the great human adventure calls us to seek out and understand each of these objects in their own terms, terms based on physical description and scientific fact. Vesta is no less interesting a member of the region between Mars and Jupiter than Ceres, just because it's not given a designation of one type or another. More than this, though, once we free ourselves from the shackle of planetary labeling, the worlds themselves begin to suggest a structure and thus tell a narrative of natural processes that form the solar system we have come about in. There are the innermost rocky worlds, made of silicates and possessing only relatively thin atmospheres. There are formational fragments left over from the period before when Jupiter gained enough mass that it could disrupt the accretion process with its prodigious gravitational influence. There are outer worlds, again numbering 4, with deep hydrogen and helium atmospheres, vast arrays of moons, and ring systems great and small. One could even subdivide these into 2 sub-classifications, with Jupiter and Saturn being in one group due to their creating liquid metallic hydrogen deep within their interiors, and Uranus and Neptune, so historically linked, lacking such a layer. Finally, there is that third zone, the objects of the Kuiper Belt, perhaps still coalescing in the billions of years-long gravitational dance of matter around our star. It is through this sort of classification, both dynamic and compositional, that I think a truer picture emerges of our solar system and the processes of its formation. So, if I haven't offended you too badly, henceforth I will endeavor to refer to the objects of our solar system as worlds and places to be explored. I think that it is the worthiest of all designations, and it places us squarely in the tradition of human inquiry and discovery. So, as I conclude, let me acknowledge a couple of sources. First, let me cite my primary source for this and the Planet Hunter episode. Thomas Levinson's recently published The Hunt for Vulcan is really a fantastic book about all of these kinds of stories, and I would really highly recommend it to anybody who would like to pick up on more of this. He tells a lot more stories than I have time to. He talks a lot more in depth about the physics and astronomy that goes into this, and I think you'll really find it fascinating. You'll also learn more about that professor in Zurich. Also, if you'd like to know a little bit more about trans-Neptunian objects, The In Our Time podcast recently did a really nice episode on those, so go over there and check it out. They got 3 really great astronomers that get together and talk quite a bit about why this designation or redesignation of planets and worlds and all of that sort of thing happened, and what some of the dynamical things going on with these trans-Neptunian objects are all about. So, highly recommended there. Next, let me give a shout out to all of the listeners in the greater Chicago area. Hello to you guys in the city of big shoulders. Thanks for taking the time to listen and to be a part of the crew. And if any of you all ever get out to Fermilab or the fission sculpture on the University of Chicago campus, take a picture with you in it and share it with us on the podcast Facebook page. Also, I have to make a couple of corrections to last week's episode. As some of you have no doubt figured out, I'm one of those people who learned English mostly through reading the language. While I do seem to have a reasonably respectable vocabulary, I don't always get the pronunciations right. It's a bit like that story Garrison Keillor used to tell from time to time on the News from Lake Wobegon, part of the Prairie Home Companion Show, about calling the people of the Nile Delta who saw the mummy exhibits Egyptians because he'd only read the word. For my part, I got 2 things wrong in the last episode. First, the little English town between London and Bath is known as Slough, not Slow, which I have to say is rather disappointing. The place where you slow down, not being called slow, that's sad. The second error is that I took a significantly more Greek approach in the pronunciation of that part of the globe opposite the parts of Europe around the Mediterranean basin. It's actually said Antipodes rather than Antipodes. Sorry about that. To all you that live down in Australia and New Zealand, Antipodes. Thanks to Andrew and Tony for setting me straight on those 2 things. Finally, on a programming note, we're once again headed towards finals week here at Gordon State, and so while I'm going to try to stick with the regular podcasting schedule, things might slip just a bit as I struggle to balance all of the end of the semester chaos and the need for my students to see their grades like 5 minutes after they finish their exams. Thanks in advance for your patience, and once we get into May, I expect things will smooth out just a little bit. In our next episode, we'll set our sails to head out into deeper waters as we look to leave the solar system and, with the Herschels, explore the vast expanse of deep space. Until then, full sails on your journey.